Hello everyone. In today's video, we're going to be going over how to evaluate integrals using U-substitution. So first off, in what situation would we want to use U-substitution? Well, and this is something that'll make more sense the more you do U-substitution. Really, you want to use it any time where you have one term with such that if you take its derivative, you'll be left with a term, so in this case we'll be left with 2x, that has the same degree as another variable in your expression. So in this case, when we take the derivative of 4x plus 5, if you take the derivative of x squared plus 5, we're left with 2x, which has the same degree x as 6x. Now, that might not make too much sense if you're not familiar with U-substitution, but just bear with me as I go along. So what I'm going to want to do is I'm going to want to take my u, and I want to set it equal to whatever that the term is that has the higher degree. In this case, x squared plus 5, right? The thing that I want to take the derivative of. So we have u equals x squared plus 5. Now, next thing you want to do is also find out what the derivative of that term equals. In this case, we have 2x dx. Correct? So now we're going to move on. Now we want to substitute u in for what we set it equal to in our original equation. So 6x times u cubed. And now we know what dx is in terms of du. We know that dx equals 2x over du. Du over 2x. So we can plug that in for our value of dx. And this is the general steps that you're always going to take when you're doing U-substitution. It's not case specific. This is what you're always going to be doing. Now, if we notice, we're dividing by 2x, and we have a 6x over here. And because dividing by 2x is the same thing as multiplying by 1/2 2x, or 1 over 2x, and multiplication is commutative, we can simply divide it out from here. So 6x divided by 2x will leave us with 3u cubed du. Now if you notice, this integral is a lot easier to evaluate than whatever we had originally. So let's integrate. Well, we have 3u to the 4th over 4, and of course we have our plus c. And now we're not quite done yet, because we still want our end answer to be in terms of x. But that's just an easy matter of substitution, because we know what u is in terms of x. U is x squared plus 5. So we plug that in, fill in the rest, and we get our answer for our integral. Now, let's see another example of where this is very helpful and necessary for evaluating an integral. Well, how about, what if I asked you for the integral of tan of x? Well, we can identify that tan is simply the sine over the cosine of x. And can't forget my dx's, right? So let's look at this. And now, if you notice, sine of x is the derivative of cosine of x. But negative sine of x is the derivative of cosine of x, and cosine of x is the derivative of sine of x. So we can do a U-substitution here. And because they're both each other's derivatives, it doesn't matter what you do the U-substitution as, both will work out. But I'll choose to do u equals cosine of x, because this will cancel out nicely. I'll be left with a 1 over u. Sines will cancel out, and you'll see why that works nicely in a sec. So what's du? Du will be the negative sine of x dx. So now let's do some of the magic. Well, I have the integral of, and what do I have? Sine of x is going to stay over my cosine of x, which I will write as u. And now what's d of x? D of x is just du over negative sine of x. So I'll plug it in as du over negative sine x. And now I notice sines cancel out, and I can take this negative and move it outside, because it doesn't matter right now. We'll just keep it here so we can remember to switch the sign. And what are we left with? We're left with negative ln, excuse me, jumped a step there. We're left with negative integral of 1 over u du. And now what do we know? Well, we know that if we ever have 1 over some variable and we're trying to integrate it, that's the same thing as just having ln of u. And of course we need our plus c because we're taking an integral, an indefinite integral rather. And now in our last step, well, we know what u is, so we just have to plug it in. Cosine of x plus c. And now, just to simplify further, we can take our negative and move it as an exponent of whatever is inside our log function. So what does that become? That just becomes ln of cosine of x to the negative first plus c. And if you know, raising something to the negative first power is the same thing as saying 1 over that something, right? And 1 over cosine x, well, we actually have a trig function that represents this. And what's that? That's secant of x. Of course, our plus c. And this is our integral of tan of x. Well, I hope you guys found this video helpful. It's always fun to go through this kind of math. And I'll see you in the next one.